Hi, Mr. T here. In this video, I'm going to look at three different spectra graphs, a mass spectra, a carbon-13 NMR, and an IR graph. And we're going to use this data to identify an unknown sample C, I've called it here. So I'll work through what are the features on the graph that can give us information, and then we'll try and identify 2 or 3 different aspects from each graph. After I've done that, I'm going to put it together in a report to justify why the molecule that I have selected at the end is the correct one. Okay, so let's have a look at these graphs for a start. So what we can see here is there is, on this graph, let me just change the color here, drawing, perfect. So on the graph here, yep, there is a peak, that is at 88. That's going to be our M plus peak, and it's at 88 NZ. There are some fragments here, but we're not going to do anything with those at the moment. The other thing we might need to just write down so we remember here is there is, at the end here, there is no 3 to 1, no 3 to 1, or 1 to 1 M plus 2 peaks. So no bromines or chlorines. Yeah, cool. So that's what we've identified from that graph. Let's look down now at the carbon-13 NMR graph. So we can see that there are 1, 2, 3, 4 peaks. There are 4 peaks, so there are 4 unique carbon environments. Now carbon number 3 looks like it's just above 60. So this is the 61 ppm peak. Now this is within the boundary for a carbon-oxygen bond, just a single bond. So there is a carbon in that environment. So peak indicates a carbon to oxygen. And then we have, of course, the one way over on the left past 165, and that one there is, what's that about? That's about 172. So 172 ppm peak. A bit messy here. That's number 4, and that shows us that we have a C double bond O. Cool. So that's all the information we can get from that, but that's good. We can start working with that. So we've got a molecule that's 88, has at least 4 carbons. We've got 1 carbon that's joined to a single bond oxygen and 1 to a double bond, so there must be at least two oxygens. Let's have a look at this bottom graph here. So there's not a lot to show here. There's this peak here. It's not very tall, but that indicates a carbon-hydrogen stretch. And then we have this one here, okay, and this is the peak at, what's that, 1,700 centimeters -1. So if we have a peak at 750 centimeters -1, so that peak indicates a double bond oxygen. That's good because we saw that on our previous one. Hey, one thing that we should note is there is no OH peaks. Yep. So that's important in this case because that shows us that this carbon that is bonded to an oxygen is not bonded to an alcohol group. It also tells us that we don't have a carboxylic acid group. So the question is, what do we have? So, well, let's add it up. So I said before that we had, what did we say? We had 4 carbons, and we must have 2 hydrogens. So if I was to go back up to the top here, okay, So back up to the top here. So let's draw 4 carbons, no carboxylic acids, but we must have a bond to an oxygen. Well, the only way we're going to do that is if we bond this oxygen to another carbon atom. And the only functional group we have that meets this requirements is an ester. Now I need at least 4 carbons, and I need to have 2 oxygens. And now we've got the associated hydrogens. So remember, what we do here is we add up all the carbons. So 4 times 12, 48. All the oxygens, 2 times 16, 32. And then we have 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 times 1 is 8. So now if we add all of this up, 32 plus 48 plus 8, we get a molar mass of 88 grams per mole. Cool, that's good. So this is most likely the molecule. So we need to justify that. But before we do, what we have to be aware of is this: we do have to have a second carbon bonded to this oxygen. We have to have a carbon bonded to a double bond. But it is going to be an ester, but actually we might recognize that there are more than one that there can be. So you could imagine you could have a CH3, an O, so this one here, CH2, CH3. And this is different because the methyl group that's attached to the oxygen, it's a methyl group in this case, it was a methyl group in the other. And on the other side we have 3 carbons in a row. So we can either have 2 carbons on either side of this functional group, or we can go the other way. We can have a CH3, CH2, CH2. Cool. No, that's just an oxygen, carbon double bond, hydrogen. Perfect. So at the moment, all 3 of these would meet the requirements. They all have a molar mass of 88. They all have a double bond carbon. They all have a carbon bonded to an oxygen that is not an OH. Remember, there's no OH present in the IR spec. There's no OH stretch peak present in the IR spectrograph. So we can start writing down some stuff here. Yeah, I don't think we're going to be able to tell definitively the difference between these. So let's write this up. But it's okay to have multiple answers at the end. So let's start the first paragraph. We're going to write about our first graph. So there is an M plus peak at 88 mZ. So the molar mass of the molecule must be 88 grams mole, -1. Cool. Looks like I spelled molecule wrong. And of. Let's correct that. Molecule, E missing on the end. Okay. So there is a M plus peak at 88, so molar mass of. The next thing, of course, we were going to talk about, there are no M plus 2 plus to M plus 2 peak. Yeah, there's no M to M plus peaks of at a 3 1:1 and 1:1 ratio. So there are no chlorine or bromine atoms present. Perfect. Okay, so we've got our next graph. There are 4 distinct, that means they're separate from each other, distinct, oh, I forgot the N in there. There are 4 distinct peaks on the carbon-13 NMR graph. So there must be 4 unique carbon environments. Cool. Also, we can say that there is a peak at, what do we say, 172 is a peak at 172 that indicates there is a carbon with a double bonded, carbon double bonded to an oxygen. Oh, sorry, a carbon in an environment where it is double bonded. In an environment where it is double bonded. Let's see. Environment. There's double bonded to an oxygen. Yeah, let's just put an example here. So it's this, right? The peak at 61 ppm. Let's go up here and change this. So I've got to make sure I put all my units correctly if I want to get excellence in this standard, because it is one of the requirements to use the symbols and units correctly. So the peak at 61 is within the carbon to oxygen, within the range of a carbon bonded to an oxygen with a single bond. Okay, that's cool. We could also say the other 2 peaks are around 20, must only have other 2 carbon atoms are around 20 ppm, so they are not bonded to an O or with a double bond. So what I'm saying here is they're not, they aren't going to have a bond to an oxygen or a double bond oxygen, and they're also not going to have a carbon-carbon double bond. So they. Okay, cool. So that was the second graph. The third graph. So, oh yeah. So we could talk about the C8 stretch. I'm not going to here. Most times I'm not going to, because it's not going to add a lot to my explanation. But what I am going to talk about is there is a prominent peak at what is it? 1,750 centimeters -1. This indicates in the stretching from stretch of a carbon bond. Carbon oxygen bond. Right. There is an absence of broad peaks above 3000 -1. So there is no oxygen to hydrogen. Let's do this capital. Oxygen to hydrogen stretching. So no OH functional group. Okay, so peaks. Let's get that correct. Peaks stretching. Okay, cool. So now I've put information in all three graphs, so all the aspects that I need to. I've made sure I put the units. Now I'm just going to summarize and put it together and say what the possible answers are. So there are 4 carbon atoms, and well, sorry, not 4. There are at least 4 carbon atoms and 2 oxygen atoms. So, wait a minute. There are 4 carbon atoms, and I'm just going to say there are from carbon 13 NMR graph. Okay, so we've already talked about it, so I don't need to say they're unique, but we do. There are at least 4 carbons and 2 oxygens. Oh, they're both in the carbon 13 atoms present. 1 bonded to with one single bonded to a carbon and 1 double bonded. Okay, so what we're saying is these 6 atoms add the molar mass. So the M of these 6 atoms adds 280 grams mole -1. So when the 8 bonded hydrogen atoms are counted as the overall molar mass of the molecule of this molecule is 88 grams per mole. So most of this information came from the carbon NMR graph, and what we're saying is there was 4 carbons and there are 2 oxygens. When I add that all up and I put the hydrogens, it gets to 88. This agrees with the 88 grams mole -1 I deduced that was worked out from the spec, from the mass spec graph. Okay, so let's have a look. There are at least 4 carbons on the carbon and 2 oxygens. Okay, so I'm going to cut this out and put this at the end. Actually, I'm not going to cut it out and put it at the end. I'm going to put it at the start. So, and I'm going to say from the carbon 13 in a graph, there are at least evidence shows, I guess, there are at least 4 carbons and 2 oxygens. 1 single bonded carbon, 2 oxygens present, 1 single bonded to a carbon and 1 double bonded to a carbon. Cool. So the molar mass of these 6 atoms is 80, but if you add the hydrogens, it's 88. This agrees with the molar mass from the mass spec. Excellent. So I put down, so that's one. I've used 2 different and integrated 2 different graphs to get to, I guess, assure that we've got the right answer here. The next thing that the 2 graphs tell us, so the next thing that the 2 graphs are the carbon 13 NMR and the IR graphs also, or both, show that there is an C double bond O present. Right, let's have a look at this. Present. So carbon 13 IR graphs both show that there is a carbon double bond. Yep, that's cool. Present. What else do we need? Okay, so the molecule can't be a carboxylic acid or an alcohol. Cannot be a carboxylic acid or an alcohol, as there is no O to hydrogen no peak produced from the O to hydrogen stretch. Wait. Did I say where that stretch would be? Oh yeah, I did in the first one. That's cool. So therefore the only type of molecule that meets all of these requirements is an ester. Okay, so we know that an ester is the only one that's going to meet these requirements. So then we draw down the 3 different esters that we might have, and I've got them at the top there. So there are three possible molecules. This could be. So we have three possible at the top: methyl methanoate, no, ethyl ethanoate, methyl propanoate, or propyl methanoate. Now you can either give the names or you can draw the structure out at the end. Now I guess we could look at the fragments, but I'm going to guess that the fragments are going to give us similar pieces for the similar molecules. So they're all esters, so they're all going to have an ester fragment that we would expect, and they're all got chains of. We have got a prominent peak at 43. Oh yeah, but that comes about from. Let me see, what's this here? 24 plus 32. And about 2 16s plus 32 plus 12 is 44, but I have a peak at 43. Oh yeah, that comes from here. So no, the peaks don't add any more information, so that's pretty much the answer and what I would get from this graph. Okay, so let's look at sample D. Let's hope that it's a wee bit more straightforward. Ooh, it looks a bit messy at the end there. So I think the molar mass is going to be somewhere here, but I'm not entirely sure what it is at the moment. Yeah. Here we can see 4 unique, right, carbon environments. Okay, so of course this one here is going to be the carbon double bond oxygen. There is no carbon double bond carbon, right, because that would be within this region here, and there is no, wait, what's this here? So no carbon to oxygen bond either. So because there's no carbon to oxygen bond, so it doesn't mean that there's not a bond of this carbon on the left to an oxygen as well. So we could have a carboxylic acid, but we can't have an ester from this molecule, can't be an ester, because we haven't got 2 separate oxygen bonds here. Let's have a look down to the next, let's just have a look down to the next graph. Oh, okay, so this is good. So the next graph has this very broad peak here. Okay, so this is an OH stretch, but it must come from a carboxylic acid group. Okay, so our OH from an alcohol is about 1/3 of the width of that one. This one here is evidence of a C bond O. Remember, anything below 1500 is just fingerprint, or we can't use it to identify. So we have these two things. So an OH carboxylic, so yeah, we must have a carboxylic acid functional group, right? So we've got this, plus we've got 4 carbons. So let's put those in. So I always start with the simplest one. There might be multiple, there might be at times 2 carbons in the same environment, but if we start with the simplest one and add it up, that might be the correct answer, and if it's wrong, we just draw it again with another carbon and 2 hydrogens. So here now we have 4 carbons, which is 48, 2 oxygens, which are 32, and 8 hydrogens, which are 8. So that gives us a molar mass of 88 grams per mole. Okay, and if we go back and look at our peak, Yes, we do have a peak at 88. There's a peak a little bit to the right of it, but I'm just going to say, look, there is an M plus peak here at 88 MZ, which of course means there's a molar mass of 88. A big peak at 60, yeah, it's kind of strange. Okay, so let's write this up then. So the we'll write it up here. So you know what I'm going to do? I'm just going to grab this first bit because it's kind of the same. So what we would say for a start is that there is an M plus peak at 88 MZ. This means there's a molar mass of 88 grams per mole. There are no... Now we could also say there's no odd number either for an amine. I don't need to, but I could put that there. So you could say there is no amine group because there's no odd number. And then from the carbon-13 right, NMR graph, there are 4 distinct peaks. So there must be 4 unique carbon environments. 3 of these peaks are below 40. So these peaks, because they're below 40, they're going to be carbon, so they will have no, these carbons have no carbon to oxygen bonds. Or carbon to carbon bonds. Right, so notice that each time I try and put some stuff that I notice is there and stuff that I notice that is not there, right? So we're doing some positive evidence and some negative evidence. I'm going to fix that up, that double bond, make that carbon big. Cool. Anything else we can note from there? Oh, wait, I haven't said about there is a peak at 181. And remember, I'm going to put the units that's on the x-axis of the graph. So there is a peak at 881. This and this originate from a carbon atom with a double bond to an oxygen. Cool. Let's correct that. And oxygen, why did I spell that wrong? Okay, so next part, what did we find out from this? Okay, right, so we had a broad peak between, let's see, 2,500 and 3,500 in the IR graph. There is a broad peak between 2,500 meters -1 and 3,500 -1. This originates or arises, originates. This originates from the stretch of an oxygen to hydrogen bond in a COH functional group. Also, there is a strong peak. And where is this strong peak exactly? Oh, that's pretty much on 1700. At 1700 cm -1 in arising from a C bond O stretch, indicating that there is a CO bond in the molecule. Okay, so this is cool. So we've got most of the information down here now. We could say, no, I don't think there's anything else we need to say. We're just going to summarize this. So we know that it's a carboxylic acid. We know that it has 4 carbons. So it's going to be a butanoic acid. We know it could possibly be this, you see. And a good way to show that we're working at an excellence level. So it could be this, which is still a carboxylic acid with 4 carbons, right? So this is methyl propanoate. But it's not, because if it was this, right, these two ones are not unique. They're in the same environment of each other, so you would only have 3 peaks. So we might just put that in there to make our explanation a bit more robust. So the molar mass, I'll start with that first, of the molecule is 88 grams per mole. We both as the the molar mass is 88 grams per mole. Both the mass and NMR graphs both the mass, I'm not sure that's right. The molar mass of this molecule is 88, as indicated from, or as is 88, is identified. That's the way. Identified from the mass graph, mass spec graph, I should say. As indicated by the mass spec graph, and from the molar mass of the proposed molecule, and the molar mass of the proposed mass of a carboxylic acid that has 4 carbon atoms. So I've got evidence up there that we can, or down here at the bottom here, that we've actually calculated that. So both the CNMR, carbon 13 NMR, and IR graphs indicate A C O double bond O bond, and the IR indicates that there is an OH that is part of the is part of a COH in the molecule. These phenomena must have come from a COOH group. So we know that there's a carboxylic acid. We know there's 4 unique carbons. So the answer, the molecule must be butanoic acid. As methyl or so the molecule could be butanoic acid or 2-methyl propanoic acid. So the molecule, as they both have a molar mass of 88 grams per mole, and have a COO group. However, 2-methyl propanoic acid only has 3 unique carbon environments, whereas butanoic acid has 4. So, however, 2-methyl only has 3, and has 4. Butanoic has the 4. The 4 indicated from the carbon-13 graph. The molecule is butanoic acid. Okay, so let's just check that we've done this all right. So both the carbon-13 and IR graphs indicate a carbon-oxygen double bond. Check, because we've got this broad carboxylic we've got this sharp CO peak in the IR, and we've got the peak all the way to the left in the NMR graph. The big broad peak means that there is a carboxylic acid, because that only comes about from an OH stretch that is part of the carboxylic acid. At this point, it could be 2 carboxylic acids that meet that requirement. We just, off the top of our head, if I drew down 2 of them, I drew butanoic acid and I drew methyl propanoic acid. But when we go back and review it, methyl propanoic acid only has 3 unique carbon environments, whereas butanoic acid has 4. So this molecule must be butanoic acid. Now make sure that you take note that whenever I go through these graphs, I write down some negative information as well as some positive information. Negative, I mean things that are missing, because that helps us narrow down what the molecule are, as well as things that are present. And then when I write out my conclusion, it's just a couple of small paragraphs, but I have to link ideas from different two separate graphs together, right? And at least 2 linkings of those. And the last thing we need to do to get the excellence is to ensure that when we write everything on here, that we're using the right symbols, that is the right symbols for our functional groups, and we are writing the right units. I'm going to go up here and fix this one, yeah, CM-1. And so I would just go through at the end and double check that I had all of those things right. And that is how we answer these questions. I hope this has been helpful.